Well, welcome back to Unboxing with Steve, and we have like a special treat today. Let's find out what it is. So, we have here, let's see. It is oh my gosh, it's a vintage final exam for Math 165 from fall 2019. Beautiful color, blue. Blue is an excellent choice. It's really calming and relaxing. It's the kind of color you want to have during an exam. 8 questions on this final. In fact, fall 2019 is kind of an interesting exam. It's sort of a transition exam because in this particular semester, it's a unique, where they had 8 problems, but they dropped 1. They changed it the following semester. So yeah, this is a nice exam. Let's see, what do we have here? Oh, it's a double-sided, really good, very environmentally friendly. Also helps to reduce weight, so when you're carrying it back, when you want to turn it in, keeps the weight down. And well, let's just dive right into it. Of course, we should start by taking it apart. So I brought some tools here so we could try to take it apart. And let's see what we can do here. All right. So we'll start at the beginning. We'll start with number 1. So let f of x, it's a piecewise function, negative x squared plus ax plus 5 if we're below 5, bx plus 2 if we're above 5. And we want to find a and b so that the following things hold. The average rate of change of the function from 1 to 4 is 0, and the tangent line to the function at 3/2 is perpendicular to the tangent line of the function at 2 pi. That's kind of an interesting choice, 2 pi. Well, let's see what we do. We'll start with the first thing. Now, there's a couple of key things here. We see this average rate of change. Now, average rate of change, that's a formula. In fact, that's from day 1 of our class. So that is our f of b minus f of a over b minus a. Of course, you have to be careful to remember there's also another thing called the average value of the function, which involves integration. That's something different here. So, in our case, what do we have? Well, it's f of 4 minus f of 1 over 4 minus 1. So we say, all right, what is f of 4? Well, 4 is below 5. And also 1 is below 5, which means that we're going to be using our first option. So we plug that in. So we're going to plug 4 into here. Now, be careful here, because notice there's a negative. Now, that's not saying take negative of the number and then square it. Say, no, take the number and square it, put the negative. So when we put in 4, that would be negative 16, then 4 times a and 5. Minus, now would be put in 1, minus 1 squared, minus 1, plus a, plus 5. And downstairs, well, that's 3. You'll notice I really like to use those parentheses. Parentheses save points because it's really important. If you don't use parentheses, you might forget that this minus distributes through to all these terms. So if we distribute that minus through, that's negative 16 plus 4a plus 5, and then plus 1 minus a minus 5, all over 3. The 5 and the minus 5 cancel. Negative 16 plus 1 is negative 15. 4a minus a is 3a. That's all over 3, which means that this becomes negative 5 plus a. Well, what do we do with that? Well, our average rate of change is 0. Now, the is, of course, is just a fancy way of saying equals. Equals 0, which tells us that a has to be 5. Okay, well, that's part of our answer. That's good. Now, we haven't used our second fact yet, and we haven't found b. So we're probably going to need to use our second fact for b. Now, this is about tangent lines. And in particular, notice it's talking about perpendicular. Well, we know lines are perpendicular if what's true. So if I have 2 lines, lines are perpendicular if the slopes are negative reciprocals. So, in other words, you find the slope of one and you flip it over, change the sign, that's the slope of the other one. Okay, well, so really this is a question about slopes, which means we want to talk about derivatives. Let's look at f prime of x, which gives us our slopes. Well, if you have a piecewise function, you do a piecewise derivative. So it'll be minus 2x plus a if we're below 5, and it'll be b if we're above 5. Now what about at 5? Well, at 5, we don't even know if the function is continuous, so we're not going to put anything. So, but it doesn't matter because we're not dealing with 5. 2 pi is bigger than 5 because 2 over pi is like 3.14. And so 2 times that is 6.28. Actually, it's 6.29, but who's counting? All right, so we're above 5. All right, good. So what do we have? Well, our slope at 3/2, well, you plug it into here. Now, I wrote down negative 2x plus a, but I really should have written down negative 2x plus 5, because we now know a is 5. So we would have negative 2 times 3/2 plus 5, which becomes, well, the 2's cancel. Negative 3 plus 5 is 2. All right, well, that's good. Then what? Well, what's our slope at 2 pi? And the answer is it's b. So we know these two numbers, 2 and b, have to be negative reciprocals, which means that b has to be negative 1 over 2. That's it. And we're done. We found a and b. Ah, nice. A good warm-up problem. So let's keep going. Number 2. Solve the following initial value problem. Y prime is equal to 2x, y squared plus 2x with y of 0 equals 1. Now, the word solve, well, that means we want to find something. And in particular, this really means in our particular situation, find y. What's our particular situation? Well, if you look at what we have here, is you see we have this derivative, and then we have other stuff that involves functions. So this is a separable differential equation. So it's interesting because the first problem was from day 1 of the class. The last problem was from the last topic we learned. So this test really has the whole class from beginning to end. And of course a couple things in the middle as well. All right, now what's the idea of separable differential equations? Well, what you really want is you want to have it so it's like some function of x times some function of y. Now, let's look at what we have. We have y prime equals 2x, y squared plus 2x. We need to rewrite it in this format. Some function of x times some function of y. Now, of course, if there wasn't that plus 2x, life is good, but there is the 2x. So life is okay. We just have to make it better. So here's the easy thing to do. We can say, let's pull out the 2x, the common thing. Then we get y squared plus 1. And now we have our function of x and our function of y. We're ready to go. Y prime, we can write that as dy dx. So we're going to think about this dx as being separate from the dy, move it across. The y squared plus 1, we'll move that across. And what do you end up with? Well, dy over y squared plus 1 is 2x dx. So that's our separation. Notice only y is on the left, only x is on the right. We're now ready to integrate. 1 over y squared plus 1. Classic. Classic. You always hope for one of these cases. That's arctangent. So arctangent of y on the other side is x squared. And remember, there's a constant, and you only need 1. So arctangent of y is x squared plus some constant c. Now, how do we solve the constant? Well, we haven't used this piece. Y is 0 equals 1. Well, how do we use that? Well, when we plug in x equals 0 and y equals 1. So we get that arctangent of 1 is equal to 0 squared plus c. Well, of course, 0 squared is 0, and arctangent of 1 is pi fourths. So that tells us that our constant is pi fourths. So we get arctangent of y is x squared plus pi fourths. And to finish off, remember we said to solve means to find y. So we've got to get rid of this arctangent. So how do you get rid of the arctangent? Well, you do the opposite of the arctangent, which means that we're going to do tangent to both sides. So we get that y is tangent of x squared plus pi over 4. And that is our solution. And then we're done. Life is good. A nice fun problem. I always like an arctangent. It just makes me happy whenever I get to see an arctangent problem showing up anywhere. Arctangent, a beautiful function. Beautiful function. Okay, let's turn over. Let's see what we have. Number 3. So we have this function h of x, f of g of x minus x squared plus g of 2x, f of x. And we're given some information in the table. So this is a case of we're really trying to understand, do we understand the rules? So we're to the point where oftentimes when we see a function, it's like, okay, yeah, we can just take the derivative. But like, well, look, let's take away the function. Do you understand the rules? All right, so we have a bunch of information in our table. And what are we after? It says find the tangent line to y equals h of x at x equals 2. Now, when we see a problem about find a tangent line, it really means tell us about h of 2 and h prime of 2. Because if we have these two pieces of information, what can we do? Well, our tangent line would be y equals our function at 2 plus our derivative at 2 times x minus 2. So that's our tangent line. So we're going to just leave this space here and write down our answer once we get there. So let's start by finding h of 2. So h of 2 would be what? Well, that says everywhere where you see x, plug in 2. So that's f of g of 2 minus 2 squared plus g of 2 times 2 times f of 2, which is f of, so we come over here, g of 2 is 7, 7 minus 4 plus g of 4 f of 2. Now 7 minus 4 is 3, so that says go here, what is f of 3? And that's 5. Plus g of 4 is 4. And then f of 2, that's minus 2. So 5 plus 4 times negative 2, which is 5 minus 8, which is negative 3. So there's our answer, h of 2. So we'll put that over here. So minus 3. So our tangent line starts y equals negative 3. And then, okay, now we need to find h prime of 2. Now if we're going to find h prime of 2, what we'll do is we'll start with our h, and we'll find h prime of x, and then we'll plug in 2. So h prime of x. Now looking ahead, we see we get a couple things happening. We get a chain rule, because we have a function g of x minus x squared inside of f. And we also get to do a product rule. So this is really testing our basic facts, our basic rules. And we like to be tested. I mean, we're taking a test. So we start the first piece, take the derivative of the outside, leave the inside alone. But now, multiply that by the derivative of the inside. G prime of x and minus 2x. Now we come to our second term, product rule. So take the derivative of the first, and notice the 2x, don't forget you have to do a chain rule there. So that'll be plus g prime of 2x times the derivative of 2x, which is 2, and then times our f of x, plus g of 2x times our derivative of f of x, which is f prime of x. So now, plug in 2. So we're just going to go ahead, and everywhere where we see an x, we're going to plug in 2. So minus 2 squared, g prime of 2 minus 2 times 2, plus g prime of 2 times 2 times 2 times f at 2, plus g of 2 times 2 times f prime at 2. All right, now we just start working our way through. Now we've actually dealt with g of 2 minus 2 squared before. That was up here. We saw that was 7 minus 4, and we said that's 3. So this is f prime of 3, whatever that turns out to be. G prime of 2, let's go ahead, g prime of 2 is 5. And then we're going to subtract 4. Plus g prime of 4, so we come up here, that's 2. So we have a 2. There's another 2 from there, times f of 2, which is minus 2. So 2 times 2 times minus 2. All right. Plus g of 4, that's 4, times f prime of 2, which is 3. 4 times 3. Now, we have to come back here. Where's f prime of 3? So f prime of 3 is negative 2. All right. So we have that's negative 2. That's 1. So we get minus 2. Here we get minus 8. And here we get plus 12. So minus 2 minus 8 is minus 10. Plus 12 makes 2. So h prime of 2 is 2. So we get negative 3 plus 2 times x minus 2. And that's our answer. For part A, we found the tangent line. Now, what about part B? It says, use the answer from part A, there's our answer from part A, to give an estimate for h of 1.9. See, what's happening here is it's trying to test, do we understand that tangent lines are good approximators for the function? So this is the tangent line at 2. And so what we have is that near 2, we can say that our function h of x is approximately whatever our tangent line is. Negative 3 plus 2 times x minus 2. Well, so what does that mean? Well, it means that 1.9, that's kind of near 2. So h of 1.9 is going to be approximately negative 3 plus 2 times 1.9 minus 2. Well, what is 1.9 minus 2? That would be, here, negative 0.1. Then we have times 2, so it's approximately minus 3 minus 0.2, or minus 3.2. And that is our approximation. All right, so there you go. So this is good. This is a nice thing. We've done several things. You know, in part A, we got to test our basic skills. Do we know how derivatives work, how there are rules for taking differentiation? And then in part B, we're like, hey, do you remember that when we have our tangent lines, they're good approximators. And there you go. That's nice. It's nice when we can combine different ideas together. All right, that brings us to our next problem. Number 4. So here we have the graph of the xy points. So here's our picture. Satisfying the equation below. So there's our equation. Passes through the point 3,1. Oh, there's the point 3,1. All right. Find the tangent line to the graph at 3,1. So the tangent line, I don't know. It's kind of hard to see for sure what it is. Something kind of like that. So we want to find this line. Find this line. Well, all right. What do we need? Well, we need a point. Check. Easy. Well, what else do you need? You need a slope. So that means we need to find our dy dx, if you will. Now the problem is, looking at our equation, we don't have y as a function of x. And in fact, we can see we couldn't have y as a function of x. See, because look, it fails our vertical line test. It also fails the horizontal line test. So we couldn't have x as a function of y. So this is not y as a function of x or x as a function of y. So what is it? Well, if we look at this equation, what do we see? It's an equation that involves both x and y. And so this is what we would call an implicit relationship, or if you like, an implicit function. Because it says, all right, there is some relationship between x and y, but we don't explicitly state what it is, which means we have to do our implicit differentiation. Now remember, how do we do implicit differentiation? Well, we sit here and we say, and we have our little thought bubble. And we say, what we're going to do is we're going to think of y as really being a function of x. So that's what we're going to do. we're going to say, okay, let's think of y as being a function of x. So we're going to take the derivative of both sides, with respect to x. Now, we could expand one side or the other, but I'm not going to. I tend to think that gets us into trouble. So let's just take the derivative as is. And so what do we have? On the derivative of the left-hand side, we have a 2. Now we have to do a chain rule. So x squared plus y squared squared. So it's the square is the outside function. So the 2 comes down in front, so that is another 2. X squared plus y squared to the 1 times the derivative of the inside. And remember, we're taking the derivative with respect to x. So the derivative of x squared with respect to x is 2x. The derivative of y squared doesn't go away because remember, we're thinking here y depends on x. So the derivative of y squared would be 2y times the derivative of y with respect to x, which for convenience we'll just write as y prime. You could have written it as dy dx. Equals, on the other side, 25. And now, similar thing. Derivative of x squared is 2x, and derivative of y squared, 2y, y prime. There we go. Now, we've taken the derivative, and the next thing is to say we have an option. We can solve for y prime and plug in the points, or we can plug in the point and solve for y prime. I always think it's better to plug the point in first. So let's plug in 3, 1. So we have 2 times 2, which is 4. Then we're going to get 3 squared plus 1 squared times 2 times 3, which is 6, plus 2 times 1, which is 2, y prime, equals 25. Here we're going to get 2 times 3, which is 6, minus 2 times y prime. All right, so there we go. Now, what comes next? Well, we just start simplifying. All right, 4, 3 squared plus 1 squared, that's 10. So here we have 40 times 6 plus 2y prime. And over here, we get, 25 times 6 minus 2y prime. Now, if we wanted to, we could do things such as, for instance, 40 and 25 are both divisible by 5. So we could cancel out a 5, so that would make that 8. And that would make this 5. And now let's distribute. We get 48 plus 16y prime, because 8 times 6, 8 times 2, equals over here 30, and then minus 10y prime. Okay, we'll move some things across. We'll move that over there, and we'll move that over there. So here 16 plus 10, that would give us 26y prime. 30 subtract 48, that would be minus 18. So y prime is minus 18 over 26, which, well, they both have 2, minus 9 over 13. Now we should kind of check to see if it's reasonable. I mean, certainly one thing is the number, well, looking at this line, it has a negative slope. So it's a negative answer, so that's a good sign. And what else can we say about the slope? Well, it's not very steep. In fact, it looks like it's below 1. See, 1 would be if I went straight this way. And so that's good. And so, yeah, it's about right. It's about right. You know, you should always sort of say, is the answer reasonable? If not, do something. But it's reasonable. Now, how do we finish? Because that's not our final thing. That's just the slope. Remember, we're after a line. So we're not done. But we've already got the point. We've got the slope. So we say y minus our y value, 1, is equal to our slope, minus 9 over 13, x minus our x value, 3. And now, from here, we box our answer, full points. Life is good. Life is good. All right. This is not, it kind of looks like an infinity symbol. It feels like a good math question. All right. Well, next problem. So number 5. Consider a function f of x which is defined and continuous between 0 and 8. So here's our function. Oh, wait, that's not our function. That's our derivative. You can see. So that's not our function. The graph of f prime of x is given in part A, and we're going to answer these questions. And notice they even bolded this here. For parts B to E, include brief explanations justifying the answers. So we can't just write down the answers. We've got to say why they're the answers. All right, so part A. Given our f prime, the derivative of f, so this is the derivative. They've said it now. Look at it. 1, 2, 3, 4, 5 times. Now, this is the derivative, so let's remember that. And over here, we want to give a sketch of f double prime of x on the right. Now, notice they're just going to say, look, make sure you got the right signs. Now, when you're making a sketch, essentially what we do is we want to take the derivative of this function, because to get from f prime to f double prime, we take a derivative. Now, how do you take a derivative? Well, you're kind of tempted to focus on these points here, the 2 and the 6. Those are the wrong places to be looking. Those are not important. What is important? We care about places like this. See here at 4, we've got like our flat horizontal tangent line. That's the key. And the other place is this 7. So 4 and 7 are sort of the key things to go off of. Now, what's special about 4? Flat horizontal tangent line means that our derivative is 0, which means we're going to cross at 4. What happens before 4? Well, look at our slopes. They're negative. Our slopes are negative. So it means that we sort of start and we're kind of moving up towards 4. So there's sort of something that's happening. We're going up, but we're negative, coming up to 4. After 4, we're positive. And kind of notice that we're starting to shallow out a little bit as we get to 7. So we kind of went up and we're sort of going down. 7, it's not defined because there is no tangent line at 7. Then notice it's really steep here. We're a steep positive, but again going down. So it sort of jumps up here and it's coming down, doing something vaguely like that. All right, so there's our graph of f double prime. Now let's go through and answer these questions. So let's start with B. Identify the intervals where f of x is increasing and where f of x is decreasing. So here we can say, okay, f of x is increasing when f prime of x is positive, and f of x is decreasing when f prime of x is negative. So what are we looking for? Well, we come here and we look at our f prime, and we're looking at a question, when is it above this line? When is it below this line? Whenever it's above, we're increasing. Whenever it's below, we're decreasing. So we are above between 0 and 2. So 0 less than or equal to x, less than or equal to 2. And we're above from 6 to 8. So 6 less than or equal to x, less than or equal to 8. When are we decreasing? Well, that's when we're below, and that is for 2 less than or equal to x, less than or equal 6. All right. Identify the x-coordinates for the critical points of f of x and classify each critical point. Now, it depends on who you ask what critical points are. If we go by what the book says, and it seems to be a reasonable place, well, there are 2 kinds of critical points. And that would be where our derivative is 0, so that would be at 2 and 6. So at 2 and 6, so this is where f prime equals 0. And the other place is here at 7. Why? Because this is where our f prime is undefined. So that's where our x-coordinates are at. So here's our justification. And now it says to classify each critical point. So we're going to classify, we'll use the first derivative test. And how does that work? Well, we're going to just draw an axis here, and we're going to put our numbers 2, 6, and 7. And we're going to say, what's happening to the function? Well, below 2, we have that f prime is positive because we're above the axis. From 2 to 6, we're below the axis, f prime is negative. From 6 to 7, we're positive. And then from 7 on, we're still positive. So we're going up, down, up, up. So that's our behavior. So what do we have? Well, that tells us that 2, because we're going up then down, that's a local max. 6, because we're going down then up, that's a local min. And 7, we go up then up, is neither max or min. And so that's our classification. All right, part D. Identify the intervals where f of x is concave up and where f of x is concave down. All right. Now, what does that mean? Well, concave up, that means our function is increasing. But what do we mean by our function? Our function of our derivative. Concave up, where f prime is increasing. That's our definition of concavity. And concave down, where f prime is decreasing. So what we're going to look at is we're going to look at our function, and here's our function, our derivative of our function, f prime, and ask the question, when are we going up? When are we going down? So let's start with the decreasing, because I think that's a little bit less ambiguous. So when are we moving down? And the answer is, well, look, we're moving downhill between 0 and 4. So 0 less than or equal to x, less than or equal to 4. Anywhere else? No. And all the rest of the time we're moving up. Now, where are we increasing? Well, we're increasing from 4 up to 7. That's true. We're also going up from 7 to 8. Now, at this point, let's not include 7 here, because it's not defined at 7. So 4 less than or equal to x less than or equal to 7, and 7 less than x less than or equal to 8. Now you might say, could we go 4 to 8? Well, no, there's some issues. First off, it's not defined at 7, and so we can't compare. But notice, see, if I pick a point here and pick a point there, I went down. So I'm not always going up between 4 and 8. And therefore, we can't be concave up between 4 and 8. So that's our answer, 4 to 7 and 7 to 8. Now, I should say, when we ask questions about intervals, we don't have to have less than or equal to. You could put less than, and you'd be fine. Last part. Identify the x-coordinates for all inflection points of f of x. Well, what's that? An inflection point is where concavity changes. So we just have to ask our question, where did our concavity change? Well, the only candidate is 4, because that's the only place where, see, because we have to go from concave down to concave up, or concave up to concave down. We're concave down from 0 to 4, and then after 4, we're always concave up. So our inflection point is where concavity changes, and therefore the answer is, we have one inflection point, and that's at 4. All right. And that's number 5. This one is actually kind of a challenging one if you look at it. A lot going on in this problem, especially with our discontinuity happening here. And, well, all right. Interesting problems. Interesting problems. All right. That brings us up to number 6. All right. What's number 6? Find the area bounded by the curves y equals x to the 4th, e to the 4x to the 5th minus 5x to the 4th, and y equals x to the 3rd, e to the 4x to the 5th minus 5x to the 4th, between where the curves intersect. So, okay, so these two curves intersect someplace. So, first off, let's see where they intersect. So, when does x to the 4th, e 4x to the 5th minus 5x to the 4th equal x cubed, e 4x to the 5th minus 5x to the 4th? Now, one thing you'll notice is that these parts match. And the other thing to note is because it's e to something, see, e to something is always positive. And why is that good news for us? That means we can divide out. Now you can divide out to cancel as long as what you're dividing by is something which is guaranteed not to be 0. And e to something is always guaranteed to not be 0. So we can divide out. Which says we get x to the fourth has to equal x cubed where they intersect. Now at this point, you're tempted to say, oh, let's divide out by x cubed. We can't do that. See, because x could be 0. So we can't just divide by x cubed. That will leave us with x equals 1. That's only 1 point. But what we can do is we can subtract x cubed across, factor x cubed out. So we get x cubed times x minus 1, which tells us that we get 0 and 1. So these are our intersection points. So our area is going to go from 0 to 1. Now, which one's on top? So how do we figure that out? Well, to figure out which one's on top, we don't look at 0 and 1 because they're equal. We pick something between 0 and 1. Let's say a half. A half is a nice number. If we look at a half, this part, again, the e to the something, is always the same for both of them. So we look at, say, a half to the fourth, that's 1 over 16, and a half to the third, that's 1 over 8. Which one's bigger? Well, the answer is the 1 over 8. So this one is the curve on the top, and this one is the curve on the bottom. Now we're ready. We've identified our bounds. We know which one's the one on the top. We know which one's the one on the bottom. So the area, the way you find that is you do the integral start to stop, a to b, in our case 0 to 1. Then you take your top curve, x cubed, e 4x to the fifth minus 5x to the fourth, subtract our bottom, x to the fourth, e 4x to the fifth minus 5x to the fourth, and dx. All right. Now, from here, if we just had that integral, couldn't do it. If we just had that integral, couldn't do that. But we don't have two individual integrals. We have one big integral. So what can we do? Well, one thing we can do is we can factor out what they have in common. So if we factor out that e to the 4x to the fifth minus 5x to the fourth, then we got x cubed minus x to the fourth times this expression dx. Now we start thinking about, okay, how do we actually go about integrating this? We go through sort of our checklist and we say, well, is this one of our 8 integrals that we know? And no, it's not. All right. Well, maybe there's some algebra here. Well, not really. Nothing jumps out. And then we say, let's bring out our best tool, substitution. And there's a nice candidate. Our nice candidate is we look for the piece on the inside. So this part right here, that's inside our exponential function. So you say, all right, let's try that. U equals 4x to the fifth minus 5x to the fourth. What would du become? Well, take the derivatives, 20x to the fourth minus 20x to the third, all times our dx. When we say x to the fourth minus x to the third, that's really close to what we have here. It's really close if we pull out minus 20 actually, because if we do that, then you get x cubed. See how you have minus 20x cubed minus x to the fourth dx. And then if you divide both sides, we'll end up with saying that minus 1 over 20 du is x cubed minus x to the fourth dx. And so now we're ready. This part there, that becomes our minus 1/20th du. So we get the integral minus 1/20th e to the u du. Okay. Now, when we do a substitution, we have to change everything. including the bounds. So let's plug in 0. When you plug in 0, you're going to get 0. All right, well, that's easy. Let's plug in 1. When you plug in 1, what do you get? You get 4 minus 5, which is negative 1. Now, this is kind of in the wrong order. So we'd like to flip it, because we always like the small number to the large number. And if you flip, well, you need a sign change. So that's good, because we already have a sign change. So we'll get negative 1 to 0, 1/20th e to the u. And now, that's on our list of things we can integrate. So we end up with, the integral is 1/20th e to the u, evaluated from negative 1 up to 0. So 1/20th, we'll just go ahead and pull that out. E to the 0 is 1 minus e to the minus 1. And that, well, that's our answer. There we go. 1/20th times 1 minus e to the minus 1. Nice. Good. Good. All right. Well, rounding our corner here. Number 7. Evaluate the limit as x goes to 0 of 1 over x to the 4th, integral negative 1 of the 5x squared minus 1, e to the power t squared, sine of t plus 1, dt. They even gave us a hint. Hint. Limit as theta goes to 0 of sine of theta over theta is 1. That's an unusual hint. I don't see how that's going to help. Well, maybe. Who knows? Let's see. Now, there's a couple of hints already in the problem. There's the word limit, which means what? Well, we're going to be thinking, oh, le hôpital. Oh. All right, good. What else? We see an integral with a function. And when we see that, we think fundamental theorem of calculus. So we're thinking, okay, we're going to be thinking le hôpital, and we're also going to be thinking fundamental theorem of calculus. So we're going to put those two things together. Now, we say, all right, if we're doing the l'hôpital, what do you need? You need a function over a function. Do we have that? Well, yeah. See, we actually have a fraction already, because this 1 over x to the 4th. We could have written this limit in the following way. Limit as x goes to 0, integral negative 1 to 5x squared minus 1, e to the power t squared, sine of t plus 1, dt, all divided by x to the 4th. And we just chose to write it here because it's more compact. Now the question is, what happens? Well, what does this go to? As you plug in x equals 0, downstairs you get 0 to the 4th, which is 0. Upstairs, you're going to get negative 1 to negative 1, because when you x equals 0, 5x squared minus 1 is 0. E to the t squared sine of t plus 1. Now, normally, e to the t squared sine of t plus 1, really, really hard to integrate, but the bounds match, really, really easy to integrate. That becomes 0 over 0. All right. Hey, 0 over 0, that tells us that we can apply l'hôpital. L'hôpital, mon ami, mon ami. It's been too long. So we apply l'hôpital. What does that mean? We need to take the derivative of the top and the bottom. Derivative of the bottom? Well, that's not so bad. 4x cubed. Derivative of the top. Well, now we apply the fundamental theorem of calculus. When we take a derivative of an integral, what do we have? Well, the answer is, let's just remind ourselves. So the derivative of the integral from some constant up to x of a function f of t dt would be f of x. But notice this isn't just x, it's a function. So if we just kick it up a notch, if we go to g of x, what does that do? Well, the answer is you do f of g of x times g prime of x. Why? Fundamental theorem of calculus and chain rule. So we're going to take this 5x squared minus 1, and we're going to plug it in everywhere that we see a t. So that's going to become e to the 5x squared minus 1 squared sine of 5x squared minus 1 plus 1. Now, that's our f of g of x, and then times it by the derivative, g prime. So that's times 10x. Okay. Now at this point we're like, well, what can we do? Well, we could keep applying the L'Hopital, but that looks terrible upstairs. That's going to take us a long time. Let's see if we can simplify. Because there are some things that do simplify. Nothing really simplifies up in this e, so we'll just leave that as is for now. Hopefully something nice will happen. The 5x squared minus 1 plus 1, that simply simplifies to 5x squared. Now, here we have a little bit. See, there's a 10 and a 4, so we can at least do this. We can multiply this by 5. Downstairs becomes a 2. There's an x. Here, there's x cubed. We can knock out a single x, so we get x squared. Now, at this point, what can we do? Well, it feels like we have to apply L'Hopital, but before we do that, we can say, hey, we haven't used our hint yet. So we should use our hint. What is our hint telling us? It says, if you have sine of something over something, and that something goes to 0, then the answer is 1. Well, what do we have? We have 5x squared. Can we get a 5x squared underneath? Well, yeah, if we multiply by 5, let's multiply by 5 upstairs as well. 5 times 5, that's 1. All right, well, what happens? Well, let's look at our pieces. This piece is going to go to 1, because that's our hint. The 5 times 5, well, that's going to go to 25. Here, how about this 2 downstairs? Well, that's going to go to 2. How about this piece? Well, what happens as x goes to 0? It becomes e to the minus 1 squared. That's going to go to e. It's a nice function. Which means all our pieces now behave nicely. So what's our answer? Well, in our numerator we got e times 25. This piece goes to 1. So that's 25 times e. And in our denominator we have our 2. And that's our answer. 25e over 2. We're done. Nice. Nice. Good. Which brings us to our last problem. Number 8. What is the maximum possible area of a triangle in the first quadrant formed by the x-axis, the y-axis, and a line tangent to the graph of y equals e to the minus x? And it shows us an example, shaded, and here's this tangent line at some point x equals a. And it says for full credit, you must show that your answer is indeed a maximum. All right, well, I wonder how to start. Probably the hint. Find where the tangent line crosses the x-axis and the y-axis. So let's start by finding the tangent line. All right, feels like we've done a lot of tangent lines in this exam. Well, that's not surprising. This is Calc 1. You do lots of tangent lines in Calc 1. So what do we need? Well, we need a point. Now, that's not so bad. If I look at this point, it's at a, comma, e to the negative a. All right, what's our slope? Well, let's take our derivative. Y prime would be e to the negative x times the derivative of negative x, which is negative 1. So, if that's our point, what's our slope? The answer is we plug a into here. So we get minus e to the minus a. So we have a slope and a point. So our tangent line would be what? Well, it would be y equals our y value, e to the minus a, and then our slope, so minus e to the minus a, times x minus our x value, a. So there's our tangent line. Now, we want to know where does this hit the x-axis and where does it hit the y-axis. So if I want to see where it hits the y-axis, well, that's also known as the y-intercept. And to do that, you plug in x equals 0. So what do you get? Well, you get e to the minus a, and then here you get minus e to the minus a times minus a, which is plus a e to the minus a, or if you like, a plus 1 e to the minus a. Where do we hit the x-axis? Well, that would be where y equals 0. Okay, so we get that 0 equals e to the minus a minus e to the minus a times x minus a. Now, we do something we did on the other problem, which says, oh, you know, e to the minus a can never be 0, so we can divide out. So if you divide out, this really becomes 0 equals 1 minus x minus a. Or, you can move this across, x minus a equals 1, or we can conclude x is a plus 1. So now we know this point is at a plus 1, and we know that that point is at a plus 1 times e to the minus a. Well, how does that help us? Well, it helps us because those values gives us our height and our base. And our area of our triangle, that's 1/2 base height. So that's 1/2. Our base is a plus 1. And our height is a plus 1 e to the minus a. Or, if you like, 1/2 a plus 1 squared e to the minus a. So now we have our function that we're trying to optimize as a function of a single number, a, which is perfect. So this is the hardest part. We've done the hardest part of this problem, which is to write what we're trying to optimize as a function of one variable. From here, it's sort of a nice, casual walk through finding critical points and testing them. So let's take our nice stroll. Start by taking our derivative, a prime. Well, we're going to have to use a product rule. So what do we have? So that's 1/2. Take the derivative of a plus 1 squared. The 2 comes down. A plus 1 to the 1 power times the derivative of a plus 1, which is 1, e to the minus a. Then plus 1/2 a plus 1 squared times the derivative of e to the minus a, which is e to the minus a times negative 1. Now, what do these have in common? Well, we can pull out a half, because that's common. We can pull out a plus 1, that's common. We can pull out e to the negative a, that's common. What's left? Well, from the first term, we have a 2. All right, from the second term, we have a minus, and we have a single a plus 1. And, well, that gives us 1/2 a plus 1 e to the negative a, and this becomes 1 minus a. Now, what do we have? Well, we look. A plus 1, when can that be 0? Well, that could be 0 at a equals negative 1. 1 minus a, when can that be 0? Well, that can be 0 at a equals 1. Okay. And what about e to the minus a? Well, that can never be 0. Well, what do we want? Well, we're after something, so we believe it should be a equals 1. That seems the only reasonable candidate. Matches our picture. I mean, if we have a equals negative 1, that's not even going to hit in the first quadrant. All right. So this should be our answer. All right. So we believe it, but remember, it says you have to actually show it's a max. So let's show it's a max. So we're going to do a first derivative test. So what do we have? Well, we need 1. All right. Well, now what do we do? Well, we plug in something below 1. So we say, what's something below 1? 0 is below 1. And we plug in 0, what do we see? 1/2. Here we'd have 1. Here we'd have 1. And there we'd have 1. So we see that a prime of 0 is positive, which means we're increasing. Now, plug in something after 1. It can be any number, like 2 or 100, just anything convenient. And really, we only care about the sign. So what happens? Well, when we plug in, say, 2, well, a half is positive. 2 plus 1 is positive. E to minus 2, positive. 1 minus 2, negative. So the result is, this is negative, which means we're going down. So 1 is a max. So that's good. So now we've done our check. All right. So finally, what's the answer? Because remember, what are we looking for? We're looking for what is the maximum possible area. So we don't need to know when it happens. We need to know what is the value when it happens. So our maximum possible area would be A at 1. So that would be 1/2 times 1 plus 1 squared times e to the minus 1. Well, 1 plus 1 squared, that's 2 squared. 4 times a half is 2. And e to the minus 1 is the same as 1 over e. So we end up with 2 over e. And that's our answer. All right. Good. Nice. And, we didn't even use this blank page on the back. All right. Well, that was a good test. Good test. And really a wide variety of topics. We hit a lot of the highlights of our test. Of course, we should put down a name. So we'll put down Yowie Duck. What is that? Oh, it's Hungarian for roughly good times. All right. And it was. Anytime you're doing a calculus test, it's always a good time. So that's it for this unboxing. And, well, look forward to the next one, because it's always Yowie Duck, as they say, whenever you're doing a calculus test. See you later.